Many thanks to PCBWay for sponsoring this video.
Good day everyone, and welcome back to DX Explorer for another video. In today's video I'm going back to an older project. Maybe some of you might not like the fact that sometimes I return to older projects, but I really wanted to go back to the 700 milliwatts minimalist transmitter. Basically it's a CW transmitter with only one NPN transistor. The original design that I made some while ago, it was based on the original schematic that I found, and it was for the 40 meters band, but I really wanted to build the 20 meters band. Basically I want to build 80 meters, 40 meters and 20 meters. I'm trying to keep a promise to my friend Vlad, Yankee Oscar 5 Bravo Delta Lima, who really likes doing DX in CW on the 20 meters band, and he likes really small and simple transmitters. So I decided to convert the 40 meters band version into 20 meters. But I cannot continue without saying thank you to my friends at PCBWay for always sponsoring the videos and supporting the DX Explorer blog and the channel. They have great PCB prototyping services, CNC, 3D printing, SMD stencils, and do not forget they also have a PCB assembly services. So if you'd like to order a PCB board for this CW transmitter as example, which is completely assembled with all the components on it, maybe you might have to tweak a little bit on the adjustments on the low pass filter or things like that, you can order an assembled version, and you don't have to worry if you don't like soldering stuff. Don't forget they have a great online store as well with a bunch of modules and a lot of other useful things for your projects. I would really recommend you do that. Have a look in the video description, you have a link, you can register for your new account and you'll get a discount on your first order. Let's start with the low pass filter because I was curious to find out if I can calculate one using standard values and still get a decent results. Not sure about the inductor, but since I'm winding my own inductor I should be fine with that. And everything else it's pretty standard values, so it would be easy to build. If I go to analysis, let me put here 60 megahertz and I will go to plot. So if I'm going somewhere around 14.060 megahertz, I have an attenuation of minus 0.11 decibels, so it shouldn't be so bad. And if I go to the first harmonic, which should be somewhere around 28.12, let's see, somewhere around there, it shows me that I'm somewhere around minus 69 decibels, so that shouldn't be bad. And I think the third harmonic should be somewhere around 42 megahertz. I might be wrong. I'm just making it up like right now, calculations in my mind, and I'm bad with mathematics. So over here I have minus 24 dB. Now I cannot be sure if this one will perform well in reality, but probably once I'm going to receive my RF attenuators, then I can measure the output and the harmonic suppression with the tiny SA, and then I'll be sure. Until then I will send this to my friend Vlad, and probably he will get on air, and if he gets reports from other frequencies except 20 meters band, then I know the filter is not good and it will have to be improved a little bit more. But as far as I'm concerned, with such a low power it should be fine, and I don't think we will have any problems with the harmonics. So anyway, let's get back to the PCB board and continue from there. Alright, so this is so far what I put on the PCB board. What I did comparing to the 40 meters version, besides the fact that I obviously changed the crystal to a new frequency, 14.060, I also started by replacing C3 with 47 picofarads. The inductor remained the same. Obviously we discovered the value for the components we need in the low pass filter, and now I have to find out the value for C4 over here. And before I jump into the next stage, I replaced the transistor with a metal can in the new design. If you remember, in the older one over here I had the plastic version, but I used the metal can for the reason that you know, the transistor, it's overheating a little bit usually, because we're kind of forcing it. So this way you can use one of these heat sinks. Of course this one, it's a little bit bigger, but you have the same version of heatsink for these metal can transistors, and it will dissipate the heat a lot better, probably will not overheat as much. But before we jump into the next stage, you have to realize I'm not an engineer, so I'm not trying to teach people anything. I'm basically making these videos trying to show you what I do, and how I discover things, and the methods that I'm using to discover, for example, the right value for this capacitor for C3. What I did, basically, I built this test jig over here, and in this side I have this variable capacitor that I'm using to discover the value for C4. I did the same thing by connecting one other variable capacitor over here, and I figured that the best value that I could use, a standard value, it was 47 picofarads, because I was trying to see with what value the transmitter oscillates properly and doesn't have, at least by ear, it doesn't have any distortions. So yeah, that's how I discovered the value. I didn't calculate the things. I'm not an engineer. I don't even know how to calculate that. Probably I think I have some books that my friend Steven sent me a long time ago, and I have some other magazines where I'm pretty sure I've seen some formulas and stuff, but I do not have the time to stay and search, unfortunately, because we have to work. Now I want to talk about something else. The difference between crystals. I remember from the past, well, I've seen that myself as well, but I also had a couple of other people that built similar simple transmitters or transceivers that I built, and in my design I was using this kind of crystal, which is a little bit bigger, but of course they could not find, or the crystals that they had available were different. You know, most common one, the 7.030 megahertz, no, 7.023, the one that is used in the Pixie transceivers. It's small as this one, and they were using that one, and they said, oh, but I'm not getting 700 milliwatts as you do. I'm actually getting like 300 milliwatts, and the reason, probably, it was the crystal. What I discovered is that this one obviously can take a lot more current, so it will give you a little bit more power comparing to this one, that you basically cannot force the oscillator too much, because the crystal will start heating up, and you either have chirp, or we'll see in a little bit in the experiment that we'll do, it will start acting crazy. So yeah, if you can, try to buy these crystals, the bigger ones. If not, well, we'll have to buy use the smaller ones, but we deal with less power. That's the difference. And we'll make an experiment on this little jig that I built right here. Let me see if I can unplug the power really quick. This jig, and over here on the test one, I'm also using the small crystal, like the one I was talking about. Is basically I replicated this circuit, the new version of the circuit, except the capacitor that I have from the crystal going to ground, in order to be able to adjust the transmit frequency a little bit. I did not have that one in the older version, but yeah, I didn't want to mess up my friend's PCB, so I decided to test it on this older version, since I have to take it apart anyway and transfer all the parts on the new 40 meters version for myself. So yeah, let's do a quick test on the power output and see the power output that we can get with this tiny crystal. So first I'm going to try to replicate basically the big crystal over here, but I don't have one for the 20 meters band. I think I have some for 14.050, but I'm not sure where they are. Anyway, I'm going to use two crystals in parallel on the transmitter, and if I start transmitting, I'm getting about 700 milliwatts, same as I was getting with the 40 meters version using the big crystal like this one over here. Now let's take one crystal away and transmit again, and we're getting 100 milliwatts, same crystal. Now what can I do in order to improve the power on this one? Well, probably I could play around with the value of C4 by adjusting the variable capacitor over here, and I'll show you now. And I'm back to 700 milliwatts. And what I did, I actually decreased the value of C4. I can even go higher if I want to, but what I'll do in a little bit, I will connect the audio from the through SDX, so you get to listen to the signal generated by the transmitter, and you'll see what happens when I'm basically forcing both the transistor and the crystal by changing the value of C4. Alright, so I connected the True SDX to the camera. Now we'll be able to listen to the sounds of the transmitter. So let's start doing some tests and see how it sounds. Alright, so I apologize for the very bad light on the meter, but I had to turn off the LED lights to avoid the interferences. So we are somewhere around 14.058 megahertz right now, and I'm transmitting. So yeah, this is basically right now I'm transmitting with the value of C4, basically replaced by the variable capacitor at this point. The same as it was when I was using two crystals in parallel, so it's like the equivalent of using a bigger crystal. Wait. Nope. Probably somewhere around there. So anyway, as you can tell, the transmitter is pretty stable. We're not forcing the transistor or the crystal. It's basically we give them as much as they can take, and that's it. But we want to increase the power output, so what we do, we lower the value of C4, and this is what happens. As the transistor is heating up, and also the crystal is heating up because they take too much current, what happens is that the transmitter becomes unstable, and it's either going lower or higher in frequency depending on the value of the of C4, of the variable capacitor at this point. So usually in all the transmitters and transceivers, simple ones that I built so far, every time I had a problem with chirp or similar to this one, what I did, I basically ended up adjusting the value of the output capacitor. Same testing by replacing that capacitor with a variable capacitor, and I play around with the value until the transmitter or the little transceiver performed better, trying to get the best power output that I could, but with less distortions and without having it act like this. So yeah, what should I do now? I guess I'm going to ask Vlad if he's happy with the 100 milliwatts, or maybe I can try forcing it a little bit. To about 500 milliwatts maybe, probably 300 after the low pass filter, or maybe the same 500 if I'm building it correctly and I don't have any losses. But yeah, this one starts lower in frequency, or yeah, or higher, and then it changes a little bit, but then it stays there. But still moving a little bit. So yeah, this is the confusion. I have to play around a little bit and decide what to do next. Maybe this is the right solution actually, because it sounds good, it doesn't seem to have distortions, so that means less harmonics on the output, so yeah. So after speaking to Vlad for a little bit, we decided that it's better to stick with the 100 milliwatts power output that we get with this particular crystal, the tiny one, but as long as the transmitter is stable in frequency, we're okay with that. Well, the man does QSOs with 1 milliwatts, so I'm pretty sure 100 milliwatts is okay for him. So I went ahead and built the low pass filter, which we're going to measure really quick with the nano VNA. So far we have the filter pretty close to whatever we calculated with LC, the simulation. So I'm going to go and change the scale here. Nope, sorry, back where I have display stimulus. Stop. I'm going to stop at 15 megahertz for now. So the filter is pretty close on SWR, at least 49.7 ohms, and it resonates somewhere close to 14.050. And if we increase to 30 megahertz and let's click start 25 megahertz, we can see the dip here on the first harmonic suppression, which was supposed to be 28 point something, 12 I believe. We'll go around here. This one is somewhere around minus 42 dB. It's not exactly what we calculated. I think that one was nearly minus 60 dB, but I think we're pretty close, and considering that we're transmitting with 100 milliwatts, I'm sure that we should not have any problems. Now I could adjust this even more, because you can tell the biggest dip, it's around 27.350, and here I have nearly 60 dB, minus 58. Probably if I would adjust the value of the 68 picofarads capacitor, I would get closer to 28.12 as as it was in the simulation. So probably I will tweak a little bit that value and find a capacitor which is closer to 68 picofarads, because none of the 68 picofarads capacitors that I have are exactly 68 picofarads. They're either smaller or bigger in value, around 68 picofarads. So anyway, I'll play around with that value, and then I'll install the filter and place it on the board, and after that we can start doing the I don't have the focus. I will place it on the board, and after that we can start playing around with the final value of C4 when we get to actually test this particular version that I built here. Alright, that's it for today. We finished the design, it's all ready. The only thing that I made differently comparing to the 40 meters version, it ended up to be only the value of the capacitors and the inductor in the low pass filter, and C3, which is 47 picofarads instead of 100, and obviously the crystal has a different frequency. Now probably in the future I would know that with a little bit of tweaking I get to modify any transmitter, or well, most simple schematics of transmitters or transceivers from one band to another one. So I learned a little bit more. Another lesson that I learned is to pay attention on the footprints of the components that I'm using, because the one for the 2N2222A was wrong, and I had to place the transistor on the board in a different way comparing to what it was, just so I get the right pins in the right place. And meanwhile I also modified the PCB board, and I updated the footprint to match the transistor that we're using, so you don't have any issues with that if you're ordering boards from now on. If you already ordered these boards, please double check over here so you connect the transistor in the right way. So yeah, I learned a couple of lessons in the today's making the today's video. So yeah, Vlad, later on in the future, if you're planning on buying a bigger crystal like the one that I'm using on the 40 meters band, you can feel free to replace this tiny one, and probably you'll end up with around 700 milliwatts power output, just as we get in the 40 meters version. So anyway, thanks so much for watching. I hope it was helpful and you also learned something together with me, even though again, I'm not a professional, I'm not an engineer. I play by ear many times, but that's why we are called amateur radio operators and not engineer radio operators. I don't have much battery left, but here's a test. Probably with the 7-8 volts that I have in the battery right now, I'm getting somewhere around 60 milliwatts and just a little bit over 100 milliwatts if I'm using 12 volts. So anyway, thanks so much for watching. I'll see you in the next video where I'm going to build the 3D printed CW key that I just received from PCBWay. Until next time, 73, and have a magical weekend from Yankee Oscar 6 Delta X-Ray Echo.